Hi, welcome. This is Clemens at Elektor. In this video we will have a detailed look at a simple light flasher circuit that can be found all over the internet. The circuit we will be looking at is the kind of circuit that you find when you search the internet for something like a car bulb or 12-volt lamp flasher circuit. I discovered it when a version of it was posted at the Elektor Labs project website. I assembled the circuit on a breadboard to see if it worked as advertised, and it does. This is one of those circuits that get copied over and over again without any explanations or technical details, because either nobody knows how it works or nobody cares about how it works. Therefore, I decided to analyze this circuit with the help of LTspice. Here is the circuit in LTspice. The lamp symbol is nothing more than a 10 ohms resistor drawn as a light bulb. To understand how the circuit works, it is best to start with the power off, when all the capacitors are discharged and the transistors are blocking. In LTspice you do this by checking the option Start External DC Supply Voltages at 0 volts. When you switch the circuit on by clicking the Run button, a 12 volts will develop on the drain of T2 because T2 is blocking. T2 is blocking because T1 is blocking, and so R1 keeps the gate of T2 pulled down to 0 volts. That T1 is also blocking is less obvious because its base seems to be pulled low by R2, while its emitter is being pulled high by D1. As T1 is a PNP transistor, it should be conducting in such a situation. But since we started with all the capacitors discharged, they can be considered short circuits at power up. Therefore, the emitter of T1 starts at 0 volts, while its base is pulled up to around 11 volts, thanks to voltage divider R2 and R3, and so T1 blocks. C1 charges quickly through D1, making the emitter voltage of T1 go up. At the same time, C2 is being charged through R2 and R3, but the power on transient has lifted both sides of C2 to a voltage of around 11 volts. The positive side of C2 cannot go any higher, therefore charging C2 through R2 means that the voltage on its negative side must drop. This voltage is also the base voltage of T1. So after the power supply has settled, the base voltage will start to drop while the emitter voltage still goes up. We can see that in LTspice if we zoom in a lot, or if we plot the difference between the emitter and base voltages. When the emitter voltage becomes about 0.6 volts higher than its base voltage, T1 starts to conduct. The voltage on C1 is now applied to the gate of T2 and it starts to conduct too. The lamp switches on. The voltage on the drain of T2 is now almost 0 volts and diode D1 has become reverse biased and no longer conducts. Because D1 now blocks, C1 no longer gets power and starts to discharge, mainly through R1. Another discharge path is through the base of T1 through C2 and R3, and the third is through the base of T1 and R2. Because C1 has become the power supply of the circuit and is being discharged, the voltages in the circuit all drop together, keeping T1 in conduction. This continues until either T1 loses bias and stops conducting, or until the gate voltage of T2 becomes too low to keep it open. In both cases, the result is that T2 will stop conducting and the lamp switches off. When T2 stops conducting, its drain voltage will jump up from 0 to 12 volts, exactly as at the beginning when we switched on the circuit. The difference now is that C1 and C2 are not completely discharged. This is unimportant, however, as C1 and C2 are both about half empty, or half full for the optimist among us. Since they have about the same initial charge, the process described before repeats, but at different voltage levels. The circuit has reached its normal operating conditions and keeps oscillating. There now remains an interesting question: which one of T1 and T2 switches off the other? Looking at the voltages in the circuit and the spice model of T2, we would expect that T1 switches off T2. The spice model of T2 specifies a gate threshold voltage called VTO of 4 volts. When T1 is conducting, the gate voltage of T2 doesn't drop below about 6 volts, so T1 switches off T2. Another issue that shows up during the circuit analysis is the polarity of the electrolytic capacitor C2. Its positive side is connected through R3 to a node that toggles between 0 and 12 volts. Its negative side is connected to 0 volts through R2. So intuitively its polarity seems right. Even if the base voltage is not exactly 0 volts, this still seems right as the average voltage over C2 will be positive. But is it? As we saw before, every time the drain voltage of T2 switches from 0 to 12 volts, the negative side of C2 swings up to about 16 volts, as it has a leftover charge of about 6 volts at the end of a cycle, and the switching transient adds 10 volts to that. After a transient, this voltage drops during the period back to 6 volts. The positive side of C2 remains almost constant during the off part of a period and drops to 0 during the on part of the period. Therefore, during a complete period, this voltage is almost always lower than the voltage on the negative side of C2. We can show this in LTspice by plotting the voltage over C2. Therefore, C2 is either the wrong way around, or it should be a non-polarized capacitor. Then there is a last thing, setting the frequency. The website presenting this lamp flasher circuit mentioned that you can change the frequency by adjusting the value of C1, the 100 microfarad capacitor. Now this is true, but changing a capacitor to adjust the frequency is not very practical. Actually, a much nicer control is R2, as it allows an almost linear period control. That's the advantage of using LTspice or another simulator. You can easily try all sorts of component values and see what works best. I plotted frequency and duty cycle graphs while varying the values of R1, R2, R3, C1 and C2, but only one at a time. This way I found that R2 is a good way to control the frequency of the oscillator. Lowering the value of R2 to about 68 kiloohms as a minimum value, and then putting a 1 megaohm potentiometer or variable resistor in series with it allows you to adjust the frequency over more than 3 octaves. Instead of a potentiometer, you could use a light or temperature dependent resistor. That way the flash rate becomes a function of light or temperature. Note that when R2 increases, the frequency decreases, but the duty cycle does so too, which may be an inconvenience. Increasing C1 instead decreases the frequency, but increases the duty cycle. This simple circuit does not allow adjusting the frequency and duty cycle independently of each other. Now that we understand how the circuit works and how we can adapt it, all that is left to do is finding a suitable application for it.